Thanks to the organizers for the opportunity to speak at this historic conference. My talk will be on a striking new phase of matter, a topological quantum spin glass. As the name suggests, this phase marries the physics of topological order with the physics of spin glasses, two phenomena which both lie outside the celebrated Landau paradigm for the classification of phases, and which separately have been at the center of many breakthroughs in many-body physics over the last 50 years or so. This phase also has consequences for information theory. It furnishes a qualitatively new mechanism for obtaining highly entangled states and for obtaining quantum memory at finite temperatures, and describes the physics of certain families of recently discovered novel error-correcting codes. Stepping back, an overarching theme of my talk will be the close relationship between the fields of many-body physics and the study of information and computation. Condensed matter physics is the study of emergent properties of systems of many interacting particles. Traditionally, this is focused on the study of materials in nature, which can organize themselves into a dazzling variety of phases of matter, and the discovery and classification of these was a defining success of 20th century quantum science. Over the last 20 years or so, this field has been revolutionized by ideas from quantum information, such as entanglement, tensor networks, quantum circuits, which have revealed qualitatively new insights into understanding and characterizing strongly correlated states of matter. Likewise, ordered phases of matter have played a big role in computation, particularly in error correction, by furnishing natural physical mechanisms for robustly encoding information. A familiar example from the classical world is that of a magnetic hard drive. In a ferromagnetically ordered phase, there are multiple degenerate ordered states, which are symmetry broken, and these are macroscopically different. These are macroscopically different magnetizations, for example, the all-up and all-down states of an Ising magnet, and these can be used to robustly store classical bits even in the presence of small amounts of thermal noise, which can flip some of the bits, but not the global magnetization. However, to encode a qubit, a logical quantum bit or a qubit, we need to protect not just against these kinds of bit flip noise, but also against phase errors, and this requires a qualitatively new mechanism. Kitaya's breakthrough realization was that different states of logical qubits can be encoded into entangled many-body states of many different physical qubits. And these entangled states are topological and locally indistinguishable, and this furnishes robustness of the encoded information to local noise. For specificity, Kitaev's toric code is defined on a 2D periodic lattice or a torus. There are, with physical qubits on the edges, there are two encoded logical qubits. All the logical states satisfy commuting X and Z checks. These are local stabilizer operators defined on the vertices and plaquettes of this model. The different states of the logical qubit, for instance, here the up-up and the up-down states, when written in terms of the physical bits, are highly entangled. And these different states are locally indistinguishable, differing only by the action of some global topological non-local operator, these logical operators which wind around the non-trivial holes of the torus. The checks of the toric code likewise define a zero correlation length fixed point Hamiltonian, which characterizes the topological phase of a well-studied model, the Z2 lattice gauge theory. This model, this phase diagram, has been around for many decades. And these code states label the degenerate ground states of the toric code model. And indeed, the topological degeneracy persists into an entire phase here. And throughout this entire phase, we have deconfined anionic excitations corresponding to violations of the X and Z checks, and the features of local indistinguishability, which endow this topological phase with robustness to perturbations, also endow the code with robustness to local noise. So, to summarize, the two paradigmatic classes of ordered phases of matter, symmetry breaking and topological order, which incidentally actually is also now understood as a type of symmetry breaking, but of what are called higher form symmetries. These allow for the robust encoding of classical and quantum memory. The symmetry breaking furnishes a degenerate ground state manifold where the different ground states are related by the action of symmetry operators. These act on macroscopically many qubits, which defines a code distance d. And we can use these states to encode k logical qubits into n physical bits. What's remarkable is that the threshold theorem of error correction says that as long as the error rate on my physical qubits is small enough, below some finite threshold PC, and as long as this code distance scales sufficiently fast with system size, then this logical error rate can be taken to 0 by increasing n, and this can be taken to 0 exponentially by increasing n. In other words, by entangling more and more crappy physical qubits, we make a better and better logical qubit. Several decades after this theoretical formulation, this result was demonstrated in a breakthrough experiment by the Google group late last year. Now, as I mentioned, our understanding of these phases of matter and the codes built on them was inspired by the study of materials in nature. However, the remarkable new quantum experiments which are implementing these codes look nothing like rocks in nature. This is a video from Misha Lukin's group on an atom array, which you heard about yesterday. Now, as we all know, a big goal of quantum simulation is to use these experiments to simulate these rocks. However, these novel experiments in these synthetic quantum devices with extraordinary control over individual quantum entities and their dynamics also call for an entirely new formulation of many-body physics, which will define the next century of quantum science. These experiments allow us to study emergent many-body phenomena in new regimes beyond what simply exists in equilibrium in nature, and indeed even in new types of geometries, such as these non-Euclidean expander graphs. For the rest of my talk, I'll focus on new regimes in many-body physics, combining these two ingredients of dynamics and geometry. First, the operation of any quantum device or the implementation of any quantum algorithm is an inherently out-of-equilibrium process. We take in some input, act on it with local operations, measurements, gates, and so on, and obtain a desired output state. From a many-body physics perspective, even if I'm not interested in implementing quantum algorithms, these platforms directly give us access to the dynamics of strongly correlated many interacting particles, far from the traditional study of equilibrium ground states. So we can ask, how do we define and characterize universal phases of many-body dynamics? I'll take a brief detour for a minute to talk about some of this, which has been a significant part of my research effort for the last several years. And the setting that we're thinking about is far from equilibrium, highly excited, so far from any kinds of ground states or low temperature states. And indeed, in these kinds of quantum circuit models, these discrete time evolutions, we may not even have energy conservation, so it may not even make sense to talk about low energy or high energy. Everything is high energy, if you will. In recent years, we've made lots of progress in understanding universal features of the dynamics of thermalization, entanglement growth, quantum chaos in closed quantum systems undergoing unitary time evolution. And we've also discovered mechanisms such as many-body localization by which systems can evade thermalization to trivial maximum entropy states. And this is necessary for observing non-trivial interesting dynamical orders at late times. An MBL system can get stuck in Hilbert space and retain local memory about its initial conditions for arbitrarily long times, either forever or for times longer than the lifetime of the universe, depending on the context. These are images from an experiment in Emanuel Bloch's group, where atoms were prepared in the left half of an atomic trap, and for the entire lifetime of the experiment, which was several hundred local tunneling times, the atoms preferentially remained in the left half, even though there was no physical barrier separating. Thus, time averages and thermodynamic ensemble averages do not agree in these systems, and the picture from Boltzmann-Gibbs that was shown in the very first lecture of this conference breaks down. This breakdown, in turn, allows us to define new intrinsically dynamical phases of matter unconstrained by the laws of equilibrium thermodynamics. A striking example of this, of such a novel many-body dynamical phase, is a time crystal, which was also experimentally observed on Google's platform a few years ago. Okay, so now coming back to mechanisms for ergodicity breaking more relevant to this talk, we know that another mechanism, if I'm thinking not of closed unitary evolution, but another mechanism for ergodicity breaking is to use measurements and feedback to remove entropy from the system. In a memory experiment, the goal is to start with some encoded state in the logical subspace and to preserve this state even in the presence of noise, which is trying to take you out of this logical space. Thus, a memory is an inherently non-equilibrium, non-ergodic dynamical process. Right? So for instance, if you create one of these surface code states on a noisy quantum simulator, then the noise is going to create excitations, these charges and fluxes, which are deconfined. You can deduce the locations of these excitations by making measurements, and then you need to apply some corrective feedback operator that can pair up these excitations, possibly over very long distances, and remove them to reduce you back to the code state. And crucially, this should be done without making any logical errors. Okay? Below the code threshold, indeed, it's possible to do this with arbitrarily high accuracy, and this threshold defines a kind of phase transition. It is a threshold transition in the ability to do this. I'll note here that this threshold transition is actually quite unusual from the point of view of usual condensed matter transitions. It is, in fact, inherently an epistemic transition. If we had perfect knowledge of the coupling between the system and the environment that's trying to corrupt it, then of course we could apply the relevant recovery map. I'm not talking here about how difficult it is to apply this map, just whether the map exists or not. I could apply this and recover the state that I encoded. Okay? But of course, I don't have perfect knowledge of the environment, and that's why this threshold transition essentially just captures, can the measurements made on the system alone furnish me with enough information to recover the state? More generally, there are many fundamental questions here. How do we define phases of open many-body quantum systems? How do we formulate notions of phase stability analogous to what has been done for gapped Hamiltonians? How do we characterize order parameters and quantumness in these mixed states? This will inherently require us to study and formulate information theoretic quantities going beyond symmetry and topology. I'll also note here that a fault-tolerant quantum computer doesn't just preserve information, but it also reliably transforms it. Can this be thought of as a robust, dynamical phase characterized by the flow of information rather than the preservation of information? The preservation of information built on the equilibrium ground state phases, what new ingredient do we need to think about these fault-tolerant processes in which information flows and gets transformed in a non-trivial way? There are many more questions and answers here, and I suspect these directions will furnish a very productive vein over the next several years. Okay, so switching gears, the second new ingredient for many-body physics that I want to consider is non-Euclidean geometry. This is motivated by a recent breakthrough result in error correction, which is the discovery of certain new families of good LDPC codes. LDPC stands for low density parity check. This is just a generalized kind of locality condition on a graph. All it's telling you is that every check, these are like the X and Z checks of the toric code that we talked about, every check should only act on finitely many qubits, and also that every qubit should only be part of finitely many checks. Okay, so this is kind of general locality on a graph. And then in a good code, the number of logical qubits and the code distance scale proportionally to n, which is the maximum possible scaling. This is the optimal scaling, which maximizes the density and robustness of quantum information. Okay? These good classical codes which obey the scaling, have actually been known for several decades, but the discovery of these good quantum codes is a recent phenomena which just dates back to a few years ago. Okay? So I just want to contrast this scaling with the toric code that we talked about, in that the number of logical qubits k is finite and d scales as square root of n. And it actually turns out that this is the optimal scaling that you can get in 2 dimensions with local Euclidean interactions. And it's proven that to get these good codes, you have to work on a non-Euclidean expander graph, and there's no embedding of this in any local planar way into a local geometry in a finite dimension. Good. So while these proofs involve fairly complicated models, I just want to give you a little flavor of what these codes look like. Okay? You can start with what's called an expander graph. This is a graph in which if you cut out any subset of bits, then the boundary or the neighborhood of that subset is going to scale proportionally to the bulk or the volume. Okay? You can imagine this locally tree-like graph, but then you want all the ends of the graph to be closed up with periodic boundaries so that you get the surface to volume scaling everywhere, no matter which set of bits you pick. We can now define generalized classical codes in this graph by simply placing bits on all the edges of the graph and by placing checks on the vertices. These are just classical codes here. The checks look like generalized Ising checks, just they're multi-body ZZZ type checks, which act on subsets of bits that are incident at that vertex. And so this code is manifestly local on this graph. We can also, the locally tree-like is easy to visualize, but we can actually also consider expander graphs, which are not locally tree-like, for instance, by looking at hyperbolic tessellations of space. Good. Now, to build quantum codes out of these classical codes, we can exploit a technology which is proved to be really powerful, which is a kind of product construction. This takes these geometries, and if this was already weird enough to visualize, you're going to make an even weirder geometry out of it by taking products of 2 expander graphs to get what's called a higher dimensional expander graph, and this has these kinds of plaquette-like objects. This is actually akin to taking something, you can visualize taking a product of 2 circles to build up a torus. Okay, so that's kind of what we're doing here. This graph is like an expander, so it's morally infinite dimensional, but it has this kind of local 2D structure, and this can be used to define a generalized toric code by placing X and Z checks on this graph, and this will again give you commuting projector models. Okay, so that's what these models kind of look like. And these models, I've simplified it dramatically. The papers which discovered these codes were written by computer scientists. The models were significantly more complicated, degrees in the hundreds of thousands, and the papers just read like theorems and proofs, okay? So the question that we've been asking over the last few years is, what is the physics of these LDPC codes? Much like some of these other more familiar codes, can we understand these models from a physical perspective? Do they define stable phases of matter with topological properties? What is the nature of the excitations? What are the dynamics of the excitations? Note that these codes have a finite code rate k, so it's already quite striking to have a stable phase with exponentially many ground states. Okay, I have 2 to the k ground states, k is proportional to n, so I have exponentially many ground states, and stability of this order, a stability of this ground state degeneracy, would imply a stable violation of the third law of thermodynamics, which may seem quite unusual, but indeed we've proved in these papers that this is indeed the case. Okay, so now I want to address one aspect of these codes today, of the physics of these codes today, which is about the thermodynamics and dynamics of these codes. And this will bring together these 2 different regimes of many-body physics that I told you about, non-equilibrium and non-Euclidean, to define this new phase. This phase is going to display a provably rugged, complex, free energy landscape with many stable equilibrium states. This is what you think about when you think of a glass. But now, each equilibrium state is also going to be highly entangled and is going to host a quantum memory. Okay, so this is a new phase of matter combining features of spin glasses and topological order. We'll show how this phase furnishes a new mechanism for quantum memory, and actually en route, we'll also prove various rigorous results which adds to the vast literature on classical spin glasses using methods from coding theory. En route, we prove a bottleneck theorem for quantum channels to obtain these results. This is an independent result which may be of interest on its own right. This theorem provides a dynamical perspective on formulating finite temperature phases of matter and their stability. And on the algorithmic side, it also has consequences for bounding the performance of certain quantum Gibbs samplers, which are very commonly studied quantum algorithms. Now, I'm going to tell you about all of this, but before I do that, I need to thank the people who are responsible. I particularly want to highlight Benedict Placke, who's a current postdoc at Oxford. He's fantastic, and he'll be on the job market this year. And I also want to highlight Tibor Rakowski, who is my postdoc at Stanford and has been my thought partner through much of my work on this topic. Okay, so diving in, as I said, a central theme of this work is quantum memory. We already discussed one mechanism for memory, which is operational in the 2D toric code, which is based on using measurements in feedback to remove entropy. Instead, for the rest of this talk, I want to focus on what are called passive memories. In this paradigm, one can obtain a diverging memory time simply by coupling the system to a bath maintained at a low enough temperature, without the need to do any active measurements or feedback. Traditionally, this way of defining a memory requires thermally stable order. This is easiest to see by returning to the 2D Ising model. This has a thermodynamic ordering phase transition at a critical temperature Tc. Below this temperature, there are two stable equilibrium states, rho up and rho down. These are the symmetry-broken states related by the action of the symmetry. And these states are separated by a macroscopic free energy barrier. So if we start in a state with a large positive magnetization, what we'll find is that we'll quickly relax to rho up, and then we'll hang out in rho up for a time that scales exponentially with system size and diverges if you take the system size goes to infinity first. More formally, one can say that the Gibbs state of the system, even though there's one Gibbs state e to the minus beta h, actually in practice, the Gibbs state of the system ceases to be unique below Tc. And there are many mathematical ways in classical statistical mechanics to sharply formulate what we mean by the Gibbs state ceasing to be unique below temperature. This textbook discusses many of these. For our purposes, it's most useful to take a dynamical perspective and rely on what's called a classical bottleneck theorem. In this, it's very intuitive to visualize. If you start with the global Gibbs state, e to the minus beta h, and you look at where it has high weight, okay? Below Tc, this has high weight on two kind of very far separated regions of configuration space with positive magnetization and negative magnetization, and one has to go through this kind of no man's land with very low weight, this bottleneck region, to get from one state to another using local dynamics, okay? So this gives you an intuitive picture for why these states are long-lived. If you start in one of these components and you do local Glauber dynamics, you're going to have to pass through this bottleneck region, which is going to be which has almost no weight in this Gibbs state, and that keeps you in this component for arbitrarily late times. Thus, in the asymptotic large system limit, there are two distinct steady states, and these define these Gibbs state components. So, to put it together, if you're talking about phases at finite temperature and wanting to get memory from it, for a classical memory, we have the 2D Ising model and spontaneous symmetry breaking. If you want to do the same for a quantum memory, then we need thermally stable topological order. And the only known way to get this requires going to 4 spatial dimensions. There are no known thermally stable topological orders with macroscopic lifetimes in dimensions 3 or lower. And in fact, there's a very close relationship between this 2D Ising model and this 4D toric code using these product constructions that I was mentioning to you earlier. In the 2D Ising model, my Ising checks have many local relations. The product of the checks around a plaquette is 1. This forces my domain walls to be these extended loop-like objects, which cost more and more energy as you scale them up. And this is responsible for the thermal stability of this phase. The 4D toric code likewise has extended electric and magnetic flux loops inherited from these domain walls. In lower dimensions, either X or Z type excitations are point-like and deconfined, and this is what destroys topological order at any finite temperature. Okay, so this now brings us to a puzzle. It is known that many of these classical and quantum expander codes that I mentioned do have robust passive memory with local decoders. This was already formulated in the original papers which discovered these codes. However, it is also known that the partition function of these models looks analytic at all temperatures. So there is no conventional thermodynamic transition into a low temperature ordered phase. Very simply, these codes Actually, every check in these codes is just independent from every other check. They can be independently violated, so you have point-like excitations. They're not constrained to form loops of any kind. And if you write your Hamiltonian in terms of these check degrees of freedom, the standard Kramer's 1A transformation, then what you find is that the partition function looks like that of a decoupled paramagnet. It looks completely boring, okay? So how do we have this quantum memory, this robust quantum memory, even as the partition function looks completely trivial? Okay? To resolve this puzzle, we realize that there's actually a qualitatively different mechanism for passive memory, which has been long appreciated in the classical context, namely spin glass order. Spin glasses are typically associated with disordered, frustrated spin models. The best studied is the Sherrington-Kirkpatrick model, which is an all-to-all Ising model with random interactions. The free energy landscape in these models look rugged, with multiple exponentially many global and local minima. And these local minima are associated with equilibrium states with asymptotically diverging lifetimes below some glass transition temperature, T glass. What's key is that this glass transition temperature need not be accompanied by a thermodynamic transition in the partition function. Okay? The partition function naively averages over all states at a given energy density corresponding to the temperature in which you're working. But actually, if you're hanging out in this well, you're going to stay there forever. You're ergodically completely disconnected from these wells here. So this naive thermodynamic average does not capture what's happening with the dynamics of the system at all. And so this glass transition need not be picked up in the thermodynamics. Finally, these minima are not related to each other by any symmetries. This is often described in the language of replica symmetry breaking. And there's many, many more local minima, including at finite energy densities, than global minima. So this is not something that's understood in the language of spontaneous symmetry breaking. In the picture of bottlenecks that I introduced earlier, there are exponentially many Gibbs state components, all separated by bottlenecks. Okay? And now the point is that if I start in some states which live in the bottom of these wells, okay, those states are stable. I can act with some thermal noise, and I'm going to live within these wells, and I can recover these states which I started with. So I can use 2 to the k wells to actually encode k logical bits, much like I was able to use the 2 wells of the 2D Ising model to encode 1 bit. So the system can serve as a robust memory encoding many classical bits. The question is, can we encode quantum memory in a similar way? Okay. Usually when people talk about quantum spin glasses, they have these classical models with a transverse field added to it. The transverse field can tunnel between these wells. But for a quantum memory, we need local indistinguishability. We need entanglement. Okay, we can't get a quantum memory by adding a transverse field to it, much like we can't get a quantum memory from the 2D Ising model by adding a transverse field. So this requires something qualitatively different. So this is where we are so far. The classical memory has there's 2 routes for classical memory, spontaneous symmetry breaking and spin glass order. This hole is purposely left in. This is what we fill. Okay, we have this new phase, a topological quantum spin glass, which allows you to get quantum memory in a manner akin to the type of memory that you get in classical spin glasses. So let me define the features that define this phase. And I want to emphasize here that we're going to prove, like rigorously prove. This is one of the first few papers I've written which have theorems and proofs in them. We're going to prove the existence of this topological quantum spin glass phase at low temperatures in a family of error-correcting codes. The features that are going to define this phase are, the first 2 features are concern the classical complexity of the free energy landscape. We're going to say first that there's exponentially many stable minima. This is called shattering. You can imagine your configuration space shattering into many distinct ergodic sectors. Okay. Actually, in these codes, because my code rate is proportional to n, I already have exponentially many ground states. So as long as I have stable wells surrounding these, this property is already met. Okay. But I want my partition function, or I know my partition function looks trivial. So in order to reconcile that, I couldn't have had just stable wells around these symmetry-related ground state copies, because then I would have seen a finite temperature phase transition. In order to get triviality, I actually need many, 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 many more local minima already within one logical sector, which has only one global minima. This is called incongruence. There are exponentially many more stable minima at some finite temperature. Okay? So these are just classical properties. bring in the quantum, we can show that if you look at the Gibbs states within these minima, by the way, to prove these, we use this quantum bottleneck theorem that I told you about earlier. So you look at the Gibbs states that live in these wells, and you can show that these Gibbs states are topologically ordered, which means that there's no decomposition of the Gibbs states purely in terms of short-range correlated pure states. Okay? So that defines this entanglement structure. And finally, if you look at these Gibbs states from symmetry-related wells, together they can be used to define a quantum memory. And in fact, you can pick different states from each logical sector and its symmetry-related copies. So there are actually many, many, many different emergent embedded quantum memories in these settings. So these new features add the quantumness and the topological to the topological class. Combining this as a summary, we see that we have these classical LDPC codes. These define classical spin glass order. This was actually appreciated in a very different language in the spin glass literature, but we obtained it using completely different methods. And then you can take products to get these quantum LDPC codes, which define quantum spin glass order. I'll just take 1 minute to make a couple of comments. First, these models may have no disorder whatsoever, not even in the geometry. These expander graphs can be obtained in perfectly deterministic ways. So there's no frustration, no disorder. This adds to the family of known spin glasses, even classically, and they might furnish insight into geometric or structural glasses, because this comes from geometry and not randomness. Our method of analysis is rigorous. We prove spin glass order and the structure of energy barriers, and actually these rigorous results are hard to come by even in very well-studied classical spin glasses. And we prove these using just 1 page of math. It's really simple. We rely on properties of codes, such as the structure of energy barriers and this bottleneck theorem that we proved, rather than anything having to do with replica symmetry breaking. So it's a completely orthogonal proof technique and much more transparent, at least to me. And one hope is that maybe this could be useful for formulating proposals for quantum memory, which do not rely on thermal stability, even in finite dimensions, for instance, in thinking about 3D quantum memories. Okay, I'll skip the key ingredient that we use, which is some structure of energy barriers, and why this arises in these expander codes, and then the kind of flow chart for how you derive this. And the summary is just that these striking new experimental developments have opened up vast new frontiers in many-body physics, particularly out of equilibrium and non-Euclidean. There's much to be done in discovering, understanding, and characterizing novel phases in these new settings, and this actually requires developing qualitatively new paradigms for phase stability and order parameters, which in turn promise new insights into novel mechanisms for encoding and processing information. This topological quantum spin glass is a striking illustration of this program of interest in its own right. Spin glasses have found applications in all sorts of contexts over the last several years, and the hope is that these topological variants will prove to be similarly useful. Thanks.
So we are open for a few questions, quick questions, but please.
Thanks for the great talk. I was just wondering, sort of a big problem in codes to decode once errors come, and sort of I was wondering if your physical insights into the physics of these good LDPC codes tells you something about why it might be harder to decode errors in those.
So it's actually it's much easier to decode errors because you can think of the system as being trapped in a well, and then you can just cool down to the bottoms of the wells. So the decoding is local decoders, that's easy. What's much more difficult is to do logical operations on these codes, because if everything is stuck in these wells and you want to actually transform the information in different states, that becomes quite a bit harder.
Can you hear me? Yeah, thank you very much also for this nice talk. So you're considering temperature fluctuations here. What if you add, for example, quantum fluctuations, for example, like a transverse field or terms like that? I guess this will also be stable, right?
Good, yeah. So the key result that helps us prove a lot of this is that these models have very, very steep energy barriers, and those actually also allow us to prove stability with respect to quantum perturbations. That also works. Yeah.
Please. Please go ahead.
If you retain a locality in a finite Euclidean dimension, and if you make a glass physically as a material, it's a metastable state.
Right.
So I think that the hope of getting thermally stable states as opposed to merely metastable ones by putting them in a glass will fall apart when the glass crystallizes over exponential time. That's probably true, but it doesn't mean this is a fascinating direction to go.
Please, yes, go ahead.
Hi. Thank you very much for the nice talk. Just a short question. Is there a way, because you're saying your partition function is analytic and everything right, and you're wondering how come that there are phase transitions, isn't it the same problem with the Li-Yang formalism of phase transitions, where you look at the complexified zeros of it, and then you, in the limit n goes to infinity, you find, oh, there's a density, and then you have jumps? That's where the phase transitions have. So can you understand what you're doing in the terms of Li-Yang zeros?
I haven't thought of Li-Yang zeros specifically, but the reconciliation is pretty transparent. It's there even in the classical problems. You have this global Gibbs state, but that global Gibbs state does a kind of average over configuration space, which isn't appropriate. But there's a sharp way in which you can formulate distinct Gibbs state components and show that each of them has asymptotically long-lived lifetime. So that's the resolution, that those are really the sectors in which you should be working. You shouldn't be doing this thermodynamic average, because the dynamics don't support that.
Okay, thank you.
Perfect.